So what happened when you have this combined loading? It means that you're going to have axial force, and this axial force could be tension or compression, right? And also at the same time, you have bending moment on the section. And here in this slide set, we are interested in both axial tension and compression. So it doesn't matter. If I give you a section and said, here's axial load, it could be tension or compression. But when it comes to pre-stress, it's going to be usually compression. So keep this in mind. In pre-stress, we do compression force. But if you are covering this subject, it can be tension or compression. Are we clear about this? All right.
Yes.
Very good. So usually when you have an axial load only, when you have an axial component only, the stress is going to be equal to P over A. Just the force divided by the cross-section area. We call this normal stress. When we have bending moment, we're going to have combination. If the bending moment, like in this direction, we call this positive bending moment. What happened in positive bending moment? You're going to have tension on the bottom fibers, compression on the top fibers. This is also going to be creating compressive stresses. So it's going to be normal stresses top and bottom of the beam. But this is not due to an axial load. This is going to be due to some applied moment. Right at the neutral axis, which in this case is going to be the centroid of this section. Like if you have a rectangle, for example, it's going to be at the mid height, right? Right at the neutral axis, just due to moment, you're not going to have any stresses. Once you start to get further away from the neutral axis, you go to the top, compressive stress is going to increase till you hit the highest point in the section. It's going to be like the top fibers. This is going to be like the highest compressive stresses. Same thing when it comes to the bottom, it's going to be the highest tensile stress, is going to be right here. So if you like to draw the stress distribution due to axial force, it's going to look like this. It's going to be uniform. Just take the axial force divided by the cross-section area, the contact area. So we say axial force divided by contact area. It's going to be the pressure or the stress due to the axial force. We call this sigma P. Just differentiate between the stress from the axial force and the stress coming from the moment source. So okay, yeah, compressive, and it's going to be going up in this direction. You see the arrow direction. When it comes to the moment, in this side, this is going to be tension in here, and here's going to be compression. So you see this direction is going to be the same as this, compression, compression. This is going to be tension. So if you just have moment, you can use this distribution for the stress. When you have axial load, it's going to be only this distribution for the stress. So this is going to be like two separate cases, right? Here is one case for axial load. Here is one case for moment applied on the section. Now, when you combine them, which means when you apply axial load and moment at the same time, now what's going to happen? You need to draw the stress very similar to what we have done here for the axial force and the moment. Now you look at 2 points. This point here, we call it point 1. Now what's point 1? It's going to be this point. What's point 2? It's going to be this point. Same thing here, point 1 and 2 for the moment or the flexure effect on the section. It's going to be here some tension, and here's going to be some compression. Now, all what you need to do the method of superposition, if you guys heard about it before, which means that you just add this to that, you add the P to the M, and also you add the stress due to the axial force at point 1, due to the stress due to moment at point 1. And same thing for point 2. You take the stress at point 2. From here, you add the stress at point 2 from there. Now, what's going to happen? I'm going to start here with point 1. I have already here compression, and here I'm going to be adding some tension. What's going to happen? Would the stress ends to be tension or compression? Someone's going to say it depends on the stress value. If sigma P in value is much higher than this sigma M, because this here is going to be sigma M and this is going to be also sigma M, it means that you're going to end up with some compression here because the compressive stress is going to prevail. But if the axial force effect, which means the stress due to axial force, is much lower in value than this, now you see I'm saying in value. I'm not here addressing, say, positive and negative values. No, I don't want to talk about this now. I want to first develop the feeling and the sense for it. So if this moment stress is going to be much higher than this axial force stress, you're going to end up with some tension here. So it depends which one is going to be larger in value, right? And this side is going to be tension. This side also is going to be compression here. So if you have lots of tension and less compression, you're going to end up with some tension at the end due to this combined loading. If you have this tension is going to be much less in value than the compression here, you'll end up with compression at this point. How about point 2? Point 2, from the axial load, I have already some compression. Now, from the moment you're adding additional compression to it, so the compressive stress is going to increase because in this side it's going to be additive, and this side is going to be subtractive. So at point 1 is going to be subtractive, at point 2 is going to be additive. So I'm going to write the equation like this. I'm going to say P over A plus or minus M divided by I times C, which means the stress due to axial force plus or minus the stress due to moment. Don't forget, I'm not addressing the compressive to be negative and the tension to be positive yet. I just say, let me put this equation like this, because someone would like to say, if I want to see the compressive stress to be negative, let me put here a negative value for F sub P. I'm going to say yes. Unless when it comes to the analysis of this stress, the P itself is going to have a negative value, which makes more sense, right? If you put this force P to be negative value, I understand. So you're going to have negative stress. So it's true, it's going to be F sub P, which means sigma P. All right? Just, we use sigma and F is going to have the same meaning. It means stress. Okay. One example. Now I'm looking here. I'm trying to figure out what forces do I have. The entire section here is given to you, and it gives here this axial force of 50 pounds, 150 pounds, excuse me. I don't see the moment. Moment is not clear to me, but the moment here is going to be equal to the force multiplied by some distance. We call this the eccentricity. Let me move a little bit here. Eccentricity is going to be that distance measured from the applied load to the centroid, which is 5 inches. Therefore, this force here, I can move it to the center and add some moment to it. So I'm going to say, here's the moment that I'm going to be adding to it. And the moment is going to have compression in this side. And how much is this moment? It's going to be equal to the force times the eccentricity. So I'm going to say moment equals P times eccentricity E. We call this E, eccentricity of 5 inches. This is true. You see the moment, it says 750 plus an axial force. So it makes sense. And after that, I can do the stresses or the stress distribution both sides, like what you have here. You see this? Due to normal force, I have a uniform stress of 3.75. Due to bending moment, I'm going to have 11.25. One side is going to be compression. The other side is going to be what? Tension. So the side is going to be C more compression, which is like point C. This point C is going to see lots of compression. The stress right here, if I may write it, the stress right at this side is going to be equal to what? It's going to be compression plus another compression. The first compression is going to be 3.75 coming from the axial force. The second compression is going to be plus 11.25. The whole thing is going to be compression. Again, I'm not talking about compression to be positive, negative or positive. I don't care about this for now. But I'm just going to call this compression. So I keep track of the signs. In this side here, the stress is going to be equal to this compression. So I'm going to say 3.75 minus 11.25. Why? Because 11.25 is going to be more tension. So most likely 11.25 is going to be more. So I'm going to say this is going to be tension. Again, don't worry about the sign for now. I don't want anyone to think and say usual compression is going to be negative, tension is going to be positive. I understand that. We're going to address this later. So this is the way it works when you have combined loading, like an axial load and a moment, bending moment on it. Oh, this is not the one. This is the one that you guys were working on, right?
Yes.
Yeah.
So first you need to find out the centroid. Any questions on finding the centroid?
No, I mean, that's fine.
So we're going to be finding here two distances. This one here, what do you call this? You can call this y top. Y sub, and then you say T or top or something like this. The other one, which is this dimension, from the centroid to here, you're going to call this y bottom.
And do we include the x portion of it, or how would we describe it? Like centered for like x bar, we don't have to include.
No, in this direction, no, you don't have to, because neutral axis give you right in the middle.
Okay.
So you don't really need to do it about this y axis. You just do it about this x axis. So the items that you're going to be solving for, first one is going to be centroid location, which means this y top and y bottom, right? So I'm going to say y top. Y bottom. Moment of inertia, which is I. I'm going to call it here Ix, about the x-axis, which is this one. And then after that, you can do S top and S bottom. What is S? S is a section modulus. S top equals moment of inertia, Ix, divided by Y top. And then also you do S bottom. S bottom equals Ix divided by Y bottom. This is great. Okay. So now I have two sources for the stresses. The first one is going to be like the axial load effect. So I'm going to say F due to P, to the axial force, equals P divided by A. I'm sure also that you can figure out the cross-section area of this. So let me put it here in the top, because you need to find out this A. Otherwise, how would you find out Y top and Y bottom? I mean, this is going to be part of your analysis at the beginning. So you're going to have a uniform stress over the entire section is going to be equal to P over A. This P is going to be equal to 20 kips. You can consider it to be compression or tension. It's going to be up to you. I did not define. But the critical part, I said the positive moment is going to be 25 kip foot, which means tension at the bottom and compression at the top. If you like to try it for both cases, tension and compression of 20 kips each, and solve it twice, because you remember I said that try to have a spreadsheet for your work, right? So you can play now with the signs the way you want.
Can you explain that one more time, please?
I said that, do you do a spreadsheet for this analysis? Did you do anything like this?
No. I'm wondering about how do you determine if the positive moment, like how it goes clockwise or counterclockwise, or
Okay, great. Okay.
I'm kind of confused about.
I'll address this. I'll say what does mean by positive moment in concrete. So let me put it here. What does mean by positive moment in concrete? Just to confirm again, when the tension is at top or bottom?
At top or the bottom? I don't know.
Please remember this. Okay. Do we have it anywhere else? I mean, have we studied this? Did we talk about this ever in this lecture? Just wondering. We call this going to be here positive moment. You see this? So
Yeah.
it's not about clockwise or counterclockwise. It's about tension at the bottom is going to be positive moment, right? So this one here is going to be tension. This one here is positive moment, right?
Okay, so that's the same way for T beams?
For any beam,
For
for
any
any section, any
Okay.
irregular section, any section that you come up with,
I
as long
see.
as you put the tension on the bottom, you call this positive moment. And look at this trick here. I want you also to be, look at this, the same thing that I just showed.
Oh yeah, okay, I got you. Thank you.
Now, no problem. Look at this. Is it clockwise or counterclockwise? It is both,
Oh yeah.
right? It is both. So it is not really about clockwise or counterclockwise. It's about tension on the bottom, compression on the top. This is what
Okay.
we need to be looking at.
Okay, thanks.
All right. So the moment is going to be causing compression here and tension on the bottom, right? Now I have all the information I need. I need to find out also the stress due to moment. So I'm going to say stress due to moment on the top. You can do it this way if you want to. Stress due to moment on the top is going to be equal to the moment M divided by S top. How about stress due to moment at the bottom? F at the moment at the bottom is going to be equal to M divided by S bottom. Great. Now you want the final stress on the top. How do you do here the final stress on the top? You say, let me take the stress, because the stress here is going to be coming from where? From two sources. It's going to be compression. So I'm going to say here F top equals FP, which means P over A that we have right here, right? Now, the top here, due to this axial force, is it compression or tension? Due to this compression force, it's going to be compression, right? So I'm going to say this one here is compression. How about the moment stress on the top? Is this here, the top? Is this compression or tension? It's a compression, right? So I'm going to be adding this to F M T, and the whole thing is going to be compression. Why? Because I assumed P to be compression. Okay, good. How about the bottom? I said F at the bottom equals FP, which means compression. I'm going to say here negative, and then now let me look here at the numerical value of this stress, which means F M bottom, right? This is F sub M. So I don't want you guys to be confused about, you think that this is F minus M minus T. No, it is F sub MT. All right? Fortunately, with what I have here, this is the best I can do for now. Now you need to compare the stresses here. This stress, two values. All right? If this compressive stress is much less than this tensile stress, you're going to end up with tension on the bottom. All right? And this is what you need to do in your analysis. This is everything that you need to do.
Okay, thank you.
How? No problem. Now, how can I do a spreadsheet for this? Now I need to assign some sign convention. I need to start with some sign convention. Otherwise, I cannot, when I'm doing here some analysis, every time I look at the beam, I'm going to say, yeah, I have tension, I have compression. At the end, this is going to be this. It is good when you have a feeling for it, so you can back check your work. But let's say for now that all the values given to you is going to be all numerical values. All right?
Professor, so for the FP, we just do the P, which is like the 20 kips over the area?
Yeah, that's it.
Okay.
This is going to be P over A, like what you have here.
Yeah.
So I need to put here a sign convention. Unless I know for sure that usually P force is going to be compression, right? Like in pre-stress. I know that usually the pre-stress force is going to be compression. It cannot be tension on the concrete itself. It is true it's going to be tension to the steel, but it's going to be compression on the concrete. Now let's move to the types of pre-stressing. The term here, pre-stress, it means it can be pre-tension or post-tension. So someone's going to say, when I say here pre-stress, Does it mean post-tension or pre-tension? You say it doesn't mean anything. It can be pre-tension or post-tension. So if you say post-tension, it is pre-stress. If you say pre-tension, it is going to be pre-stress. So both of them is like two pre-stressing methods. Difference between the two: in the pre-tension, you put tension on the cables before you cast the concrete. In post-tension, you put the concrete first and then you do the tension second. The videos that I have showed you here, that was inside a factory for pre-stress, it was all about pre-tension. This one you have the mass production. And this is gonna be like the typical. If you like to buy it from someone, it's gonna be like, most likely it's gonna be pre-tension. How does it work? We're gonna put this abutments. It's gonna be very strong. You're gonna have this rigid floor. Most likely it's gonna be concrete. And this is gonna be made out of steel. You're gonna put the cables, apply the tension, and as you have seen in the video, right? They cast the concrete like in pieces because it's gonna be very long, maybe 200, 300 feet, and then they cut. After the concrete hardened, they come and burn the cable or they just cut it. Here's the steps. So first, you have the cable, you put the tension, you pour the concrete. Now, when you pour the concrete, has the pre-stress force has been transferred to the concrete beam yet? I'm gonna say no. It is just in tension, and the entire force just goes to these two abutments. Now, after you cut the concrete, you cut the steel here or the tendon, what's gonna happen? The force is gonna get transferred to the concrete. As if you put here two big compressive forces, one at each end of the beam. Now, what do you expect? You're gonna have an axial load and moment. So this is gonna be equivalent to what? An axial force like in here, right? And a moment. And the moment is gonna be acting like this, with compression at the bottom. So the arrow is gonna be in this side, right? So what do you expect? The beam would like now to camber. It wants to go up. You see, it is lifting up. Does it make sense? Yes? Any questions on that?
So just theoretically speaking, if you were to do that on the top, would it like camber the other way?
Yeah, absolutely. This is correct. Absolutely.
Cool, I understand.
So here's the moment direction. This is good. Let me keep this. I'm gonna keep on copying it and using it, right? So this is gonna be here, the beam moment that you have on the bottom. And this is gonna be again creating camber because you put the compression here at the bottom, right? When you put the compression on the bottom, this is equivalent to a moment and an axial load. And this axial load right now is gonna be right at the centroid, if you like to do your analysis. If you look here at this distance, which is from the centroid to the point of the jacking or the point of pre-stress, let's say here's the centroid. So this distance from here to there, this is what you call here E, the eccentricity. So I'm gonna call this to be the eccentricity. Usually we use the term E for it. And this moment, if you like, this applied moment, I'm gonna put it here. This moment is gonna be equal to P times E. And what is P? P is gonna be this axial force that you put in there. Whatever axial force that you decide on, you put it there, you're gonna be cambering it because you expose it to, is this now negative moment or positive moment?
Negative.
Negative moment, absolutely. Why? Because here is a positive moment. Positive moment doing tension at the bottom, compression at the top. Negative moment is going to be the opposite, the other way around. Okay. Now, the beam here is going to start to lift up. Now, is this beam kind of supported now in two supports or not yet? I say not really. Is it in use? No. We didn't use it yet. Do you have any service loads? You guys know the meaning of a service load, right? Like they use the occupancy load. It is not loaded yet. Nothing there yet. So the only loads that acts on it now is going to be the self weight of the beam and the pre-stress. So right now at this stage is going to be what? Self weight plus pre-stress. That's it. This is the whole thing that acts on it right now, right at the initial pre-stress. Now, you guys, you understand that the concrete is going to start to get shortened a little bit, right? Because the axial compression, you know that. When you expose any material to high compressive stresses, it's going to get a little bit smaller. I'm not talking about a few inches, I'm talking about maybe 1/8 of an inch. So it's going to be very similar, very small value. But this small value is critical when it comes to pre-stress. Because if you like to figure out the amount of force that you put there, you can just look at the cable. Here's the cable length, right? At the beginning. Forget about before we start to put the tension. Let's say here's a cable, right? That was the length of the cable. Now what you do, you're going to apply some tension to it. Now you stretch the cable. With the change here that you can call delta L, you divide by L, the length of the cable, you can figure out the strain. Take the strain and then go to the stress-strain relationship, you can figure out the amount of stress in the cable. This is still within the cable, right? Or the tendon. Take this force or this stress multiplied by the cross-section area of the cable, you can figure out the amount of force P. So what happened in the site, they start to apply tension to the cable, measure the amount of displacement or extension, divided by the total original length of the cable. With that you have the strain multiplied by E. You know, E, the modulus elasticity. With that you get the stress. Take the stress multiplied by the cross-section area of the cable, you get to the force, which is P. Now you can work on the beam. You can say this force, it is true, it's going to be like tension in here, but it's going to be compression on the concrete. Now again, the concrete is going to start to shorten a little bit, which means that you're going to have some losses in the strain. The amount of strain that you applied, the extension that you applied here to the steel cable is going to get reduced over time. Also, the concrete is going to shrink. You know, concrete is a shrinkage material, right? It's a shrink material, which means the size of the beam itself is going to get a little bit reduced. There's going to be additional loss. Also, the steel itself is going to start to relax a little bit. And also, some slip may happen at the anchorage. You see this anchorage point? You may have some slippage at this point, which means that you're going to be losing this amount of stress that you put on the rebar, and therefore you're going to be losing the force P. You're going to be losing a little bit of it. This losses is roughly between 10% to 15%. So when you apply this pre-stress at the beginning, let's say that you'd like to apply 100 kips, right? So you know eventually this 100 kips is going to reduce to 90 kips because you have your 10% losses. We call pre-stress losses. Maybe you should have a start by putting a tension force to it of 110 kips so that when you lose the 10 kips, you'll go back to the original desired value. Does it make sense?
Yeah. Wait,
Yes.
Professor, so that 10%, 10-15%, that's taking into account all the losses?
Yeah, all the losses.
Oh, okay.
Yeah, and there is lots of studies and analysis of these losses, and I'm going to show you at certain point what the code says about. So I'm going to say, meaning that I'm going to have initial pre-stress force, and then eventually I'm going to have effective pre-stress force. Does it make sense? I'm going to say initial pre-stress right? What's the initial pre-stress? It's going to be the amount of tension that you're going to put here. Because don't forget that also this abutment, they can move a little bit, who knows, right? And you're going to have some anchors here. And then you can lose also, you can have here some losses during this production process. So this is going to be here initial pre-stress. And then finally, when you leave this concrete beam, the pre-stressed concrete beam, you leave it there for a few months before you take it and ship it to the site. You're going to have plenty of losses. You're going to have the effective, I'm going to call it here the effective pre-stress. So the force itself that you put there is going to be called effective pre-stress force, if you like. The top one here, I'm going to be using P sub I. So it's going to be PI. P sub I is going to be the initial pre-stress force. The effective is going to be called here P sub E. So it is not P times E like in here, right? This is eccentricity. It's going to be called P sub E, the effective pre-stress. And how much is the difference again? Let's say 15%, maybe 20%. It depends on the quality of the work that you do there. Of course, you don't want to see lots of losses, right? You'd like to reduce it as much as you can. So now, when it comes to the pre-stress, we're going to have two forces that you need to work with. One of them is going to be the initial pre-stress that you start with. And the other one, it is after you leave the concrete member, the pre-stressed concrete member for a few months in the yard, and then you come and pick it up, take it to the construction site, it's going to be P effective. Any questions?
Yeah, is the type of concrete used in pre-stress different than the kind of concrete they use in
Yes,
just regular?
absolutely. They try to use non-shrink concrete, so they put some additive to reduce the shrinkage. This is going to be very important. And also, usually it's going to be high strength concrete. So the minimum is going to be 5,000.
Okay. And then also, like,
Go ahead, Chris.
because you don't want any cracking, right? Because if it cracks, I was gonna say, if there's any cracking in the concrete, then that kind of, you lose the pre-stress, right?
This is true, but why cracking is going to happen?
Because the concrete's too weak.
Yeah, but cracking is going to happen when the concrete is exposed to tension.
Yeah.
So you may have some cracks here on the top. If you didn't do good calculations, you may have some cracks here, right?
Mhm.
But at the bottom, there's no cracks. Because actually, if the concrete wants to crack, this compressive force is going to close all of these cracks. And this is one of the benefits of using pre-stress, is going to be crack-free if you want to.
Got it.
All right.
I have a question, Professor. So
Yes.
P, you said is just the self-weight of the concrete here in this situation, right?
P
Yes.
is this force. Did you see this? P is this force, right?
Oh, I see. So we have a force there. Okay.
The pre-stress force here is PI. You see what happened? First, you put this PI. And then once you trim this right at this point, the force is going to get transferred to the beam. Right here, the force is not at the beam yet, right?
Right.
The beam doesn't see any pre-stress. But once you cut this, just once you trim it, something you can do it with a grinder. You can just burn it if you want to, right? Once you cut it from both sides, now the force is going to get transferred to the concrete. And they call this is going to be like the transfer time.
Right. I didn't see that force. Now it makes sense.
All right.
Thank you.
No problem. Now, the question is, when do you think we're going to be cutting this?
After the concrete cures?
Yeah, by how much? Do you want to leave it 28 days?
No.
Usually concrete reaches the full strength at 28 days, right?
Yes.
Mhm.
If you ask the precaster wants to cut it right after they pour the concrete. Because they need the space, they need the yard, they need to cast more concrete, right? They need this bed. This is like a big cost for them. This is gonna be their only workspace. So they'd like to put the concrete here, put it, cut it, take it out. But when do you think they can convert it? It needs to reach certain strength, right? You cannot just cut it at any time. If the concrete was poured, let's say a day, you cannot do the transfer. You cannot cut the cables and take this piece out. You're gonna be destroying the concrete. So it needs to gain certain strength, not the full strength, but there's gonna be a value that we needed there. So at the time of transferring the pre-stress force, the concrete needs to have enough strength to be able to take this force. Otherwise, you're going to break it before even you take it out, right? Okay. How about the second method? We call this post-tension. And here's a question for you. Which method is considered to be pre-stress? The pre-tension or the post-tension? Or both of them?
Both.
Both, yeah, right?
Both.
It's just the method of pre-stressing, right? This is one way to do it. Usually when you have like a yard or a factory, and this one usually, I'm saying usually, you do it in the field. But in some cases, you have precast members with some conventional reinforcement, like non-pre-tension reinforcement, like the regular rebars, and then they do it in the factory, and then you take it to construction site, and then you put the tension to it. You're gonna see this usually in bridges. They do it that way. So what happened in post-tension? You have the concrete, you cast it. So you see here, you have the beam already. Beam is already there. Now we have it. Look here. Beam is not there. The tension was there. And then the tension is there, and the beam will start to cast it. Concrete is still fresh. And here's after the concrete hardened, we cut the cable. Now look here. You have the beam. And then you have this empty duct. It's gonna be like a very small pipe, if you like a conduit, you know, the electric conduit, or a pipe, very small, flexible pipe, PVC or plastic. And then after that, they thread, or actually they don't really thread the cable, because this hollow duct, it comes with the cable. So the cable comes like shielded, you know, it has this duct around it, and you just put it there. Now after that, they start to pull the force from both sides, and then put an anchorage. You see this anchorage? They're gonna start to put it in. And you see the way you do it usually, they drape it. You see this drape, we call this draping. It's gonna look like this. It's not gonna be straight, most likely. If you do it on the side, it's gonna be like this. So here's gonna be right at the mid-height, and here's gonna be coming down. In the factory, they do it straight. Does it make sense to you guys? Why would they make it straight?
Easier to control the
Exactly.
depth.
Exactly. So if you like to do it this way, you need to come here and push down at this, right? You need to put something here to hold it down at the floor. And this can just take the floor and fly in the air. It can just do big damage. So this is cheaper. So when you do a design like this, you need to take care of this in your calculations, right? So in here, at the end, you're gonna see here that the pre-stress force, it happens right in, if you look here, it's gonna be in the mid-height of this section. Which means at this point here, you don't have any moment. If I take this here piece, and don't look at this piece, please. Just take this piece here. What happened? You have axial load, no moment, right? But when it comes to the middle, now where is the pre-stress force? Pre-stress force is gonna be here, right? It's gonna be a similar case in analysis. This case here, or this section, is gonna be like here, right? Like when you have some eccentricity. So at the beginning, no eccentricity. In the middle, you're gonna have some eccentricity. So think about this cable here once you start to pull it. As if you are pushing this beam up. You're gonna be also cambering it, which is very similar to what you're doing here. Now I want you to think about this. You have some given loads, and the load was gonna bring all of this down, right? You have some given loads, and the load's gonna be coming like this. You know that. Lots of loads. This loads wants to push this beam down. It wants to camber it, it wants to deflect it down, right? It wants to sag. And this pre-stress is doing the effect, the opposite effect to it, right? It is pushing the beam up. It is counteracting the effect of these loads. And this is the theory behind this pre-stressing. This is the idea behind it. That any given load wants to push the beam down. Now we're gonna try to balance this load by pushing it up for you. So at the end, deflection is gonna be controlled. You're gonna have very small amount of deflection, right? And the stresses on the top of the concrete is gonna be much less. Okay. Any questions so far? On difference between pre-tension and post-tension?
So post-tension don't use actual rebar, you said, but what about pre-tensioning? Like, is that rebar?
You put some
That
rebars,
get
but you don't put a whole lot. In both cases, I mean, in this case, in pre-tension, you'd like to reduce the amount of rebars, the conventional rebars, as much as you can. This is like general statement. In pre-tension and post-tension, they like to reduce the rebars, right? They just want to, all what they want to do, they want to apply the pre-stress and let go. And they'd like to reduce the amount of work by people. So they are not interested in putting lots of rebars, unless when it comes to design, you really need to put some non-tension steel, like the regular rebar. All right? Also, in post-tension, you can do like continuity. You can provide this continuity. You have a couple of spans, and look what happened. Right in the middle, we're gonna bring the cable down. In the top, we're gonna bring it up, right? Why? Because you'd like to counteract the effect of this given loads, like the service loads. Did you guys, did you study something called elastic line theory? Anyone has taken it? In structural analysis, or maybe advanced structural analysis? Elastic line theory. No?
I don't think so.
Okay. Have you studied calculation of deflection and deforming shape of a beam?
Yes,
Deflection? Yes. I'm sure that you have seen something about deflection and deforming shape.
Yeah.
Okay, good. So usually we try to match the deflected shape or deforming shape of the beam when it comes to putting the cable, just to be efficient. So if you see here, if you put some loads, the deforming shape is going to look like this. So the best way, you put the cable very similar to the deforming shape. You don't put it opposite. Because imagine if you put this upside down, what's going to happen? This pre-stress force is going to be acting on the beam very similar to the loads, right? Just imagine that you put this upside down, right? It means you're going to be pushing the beam in this direction. And also the load's going to be pushing in the same direction. So you're going to be breaking the beam quickly. There's no resistance. There is no really use of the pre-stress in this case. Look at deforming shape when it comes to continuous beams. It's going to be looking like this. Just look at any deforming shape, any deforming beams, you're going to be looking exactly like this. I want to show you here something for quick about this pre-stress. I like the illustration. This is going to be precast pre-stress. It's going to be like the cable location. You put the cables and look, I want you to look at this. It's going to be like the cable or the conduit, right? It looks like this corrugated sheet and it comes with grease and everything. So what do? You bring this precast, this is going to be a part box section of for a bridge. Here's the way it looks, and here's a cable. It comes like this with this drape, right? Now it comes with all of this. All of this is going to be embedded in the concrete. When they ship it, it's going to be like segments. It comes as segmental. They call this segmental. And then after that, they're going to start to put tension on the cables. Look, here are the cables. And they're going to put this anchor. This is going to be like an anchor piece. And you see this, this piece is here. This is what they call the barrel anchor. They're going to put all of them in one side. And now they're going to start to put this guy here. They're going to start here to pull. And of course, this anchor, they're going to put it from both sides. So if they put this anchor in here, on the other side, they're going to put exactly the same anchor. Now this is going to be the jack. And this is going to be a hydraulic jack. It works with oil, pressure. You're going to have in and out for the oil. Now look what they're doing. You start here to pull the oil and take it from here. This is gonna be the return. Put tension on the cable. The other side now is locked, the other side of the beam. And once you do this, they push this back. During this process, there is some losses. See, during this process, look at this. Just imagine you pull this here, and now you try to put this quickly. Look what happened. You try to push this anchors back quickly. You see this? During this, right at this instant, right at this moment, you have some losses. Now they take everything out, and then they cut it. Now you have pre-stress. You can also grout this, because look at this. Before you do this grout, you have, there is no contact or bond. Look at this. You don't have here any bond between the cables and the duct. You look at this. In some cases, they leave it without grout, but this is not advisable because of the corrosion. You'd like to fill it in with grout. So first they clean it with air. You want to be sure that everything is very clean, and then they start to pump the grout in. This connector here, this type of connector, was developed by a guy, his name is Fressinet. Fressinet is also a very famous company. This is a French company. They work on pre-stress. But now everybody's doing it, you know. Any company now can just take it and do it. You know, after 25 years, this technology, you can just copy it. And then they cap it, they cover these caps. Any questions on this little short
What is the
video
use
of
of
this?
the red springs, Professor?
Oh, the red spring, very good question. Now imagine what's gonna happen. You have big compressive force right here, right?
Right.
It wants to open up the concrete. What's gonna be taking this tension? Because if you put compression here, you should expect tension up and down in all directions, right? Like
Oh,
radially.
right. Right.
So
right.
this part here, this is gonna be helping you to control the amount of force that you put in here. And this is not gonna be it. This just comes with the anchor, with this Resonate connector. It comes with it. But also you can see lots of reinforcing in this location, like ties and things like this. Otherwise, you can just break the end of the concrete from this pre-stress business.
Interesting.
Good question. Thank you. More questions on the pre-stress, on the post-tension process? No? We're good? How about in concrete slab? Like regular concrete slabs? Two-way slab. I'm sure that you guys hear about this. In buildings, we do here two-way slab, right? Post-tension. Let me put another idea here for you. Here we go. Here are the columns. Then you start to put the reinforcement, conventional reinforcement in both directions. And then after that, you start to put the cables. This is more reinforcement. At the column for punching shear. And then after this, you put the other reinforcement, as they say here. You put the chairs. This chairs is just to support the bars in both directions, the top bars. And then you start to lay the cables, the tendons and the cables. And of course, you can again drape it, because this is here continuous. Look at the drape. At the bottom, in the middle of the span, it goes at the bottom when you have the tension. Here, when you have the tension on the top, you put it here on the top. And then you put it in both directions. In reality, cables don't fly this way, right? People just carry it and put it down. So you have the cables, and then we start to put some reinforcing. This is not the reinforcing, this is just for pumping the grout. This tubes is just to pump the grout. Do you pour the concrete? Any tension yet? Any pre-stress?
No.
No, not yet. Pre-stress is not there yet. Take the form, strip the forms, Now you have this piece here that later on, they're gonna be filled with grout. They're gonna put the anchors. You see the anchor is a little bit different, but the same barrel thing. You see the jack is much smaller. This jack is much smaller, and this jack is, it's not really expensive. This jack is about maybe like 10 grand or something. And this pump, this is very simple pump, oil pump. You put it to a certain pressure, measure the extension to figure out the amount of strain, and check the stresses, apply the stresses right on the side. Then after that, they come, they cut it, the grinder, and then they fill it in with grout. After that, they start to grout here to pump the grout through the hole. If you remember that thing, they need to fill it with grout to be sure it's really solid. But first, they need to clean it, as it says here, bleeding air for cleaning, right? After they clean it, they start to fill it in with the grout. They pump the grout till the comes out from the other side. Now they are sure that it is 100% filled with grout. Then they cut this. And as you see here, they go to the second floor and so forth. Any questions on the process, the technology itself, how it works? Difference between pre-stress and pre-stress concrete in terms of post-tension and pre-tension.
Does adding the grout into the ducts transfer any force from the post-tension or post-tensioning, or is it all just to protect it from water, protect it from rusting?
Now, remember that the force has been already transferred at the end of the beam. So in pre-stress, in post-tension, once you apply the force, now the force is here, right? You have already the force here, correct? The force is here at the end.
Yeah.
The force doesn't happen throughout the length of this beam. Now, after this, you're going to be grouting it. But this is not going to change the fact that the pre-stress force is already in here. Over time, when you have some losses, maybe you're going to have the force of transfer is going to happen maybe in the first, I'm going to say maybe 2 to 3 feet, and that's it. After that, no. The force is already at the end. All right?
Okay. Does the grout keep it from like the explosive like tension force if a contractor like accidentally cuts it, if they're coming back through for plumbing or whatever?
Yeah, it is stopping it. Stopping it. Absolutely. It's going to
Okay.
help to stop it. Yes. Let me put this here for you. Do you guys hear it? You hear the video?
Yes.
Yeah.
Okay.
Okay, now here is our typical stop end that would be used to orient the pre-stressing strands that we would use to apply that compressive force to the beam end. Now note, these strands are not tension, they're slack, so there's no danger here. You must be very, very careful with fully tensioned pre-stressing strands because there's a massive amount of force that can be contained in each of these strands. This particular strand, in fact, we would actually tension up to a load of 209 kilonewtons in just one strand. So what we would do, these strands would be jacked up. They would be pulled back and they would be essentially stretched. They would be put into that very large amount of tension, 209 kilonewtons for these. The concrete would be cast around the strands into the appropriate cross-section. Once that concrete has reached the specified strength, the specified compressive strength, then the strands would be gradually released, thereby transferring that force that was in the strands when they were stretched into the concrete. So that very large force in the strands would be then applied as compression into the beam itself. Now, notice with this strand layout, there's a far larger number of strands closer to the bottom of the beam. The bottom of the beam, the soft of the beam would be just 50 mil underneath the actual bottom of the strand, 50 or 60 mil. The reason for that is not only do we want to apply compression to the beam, we also want to apply a bending moment to the beam as a result of the pre-stressing operation. So because that overall position of the strand is eccentric, it's removed from the centroid of the beam, that enables that application of pre-stress to also apply a bending moment that will counteract, will act against and relieve the bending moment that results from the applied loads. The load.
Does this make sense? Yes?
Yes.
Yeah.
Yes.
What we were just talking about, right? That whatever that you do here, this pre-stress is going to be counteracting the effect of the applied loads. So you're balancing it. And this is a term that you'd like to use. We say we are trying here to balance, right, the service loads by doing this pre-stress. And this is the whole theory.
That will be applied to the beam under working conditions. Let's step back over to the finished beam itself and go through the final steps of the final aspect of how a pre-stressed bridge beam works. Okay, so this beam is one of our finished products. This was actually cast not long ago on this bed itself. Now, you'll notice there's a bit of a gap between the soffit of the beam and the actual bed itself. This is a result of what we just spoke about. When we apply that compressive force from the pre-stressing tendons, pre-stressing strands, not only do they apply that beneficial compressive force to the beam, but they also apply a moment that relieves the moment applied under working conditions. So this moment that's applied by the pre-stressing operation results in the beams actually cambering up. The beam will actually lift
You
up
see, guys, you can see
several
you can see
millimeters,
across.
10 millimeters, whatever the case may be, depending upon the beam and the pre-stressing amount and layout used. It will actually camber up. Now, this is beneficial with regard to deflection checks as well, too. Generally, for bridge beam design, we don't need to carry out rigorous deflection checks, but from an aesthetic point of view, you don't want a beam visually sagging on site. So this natural camber that results from the pre-stressing operation itself will help eliminate the potential that that beam would be visibly sagging on site as well, too. Finally, you'll notice as well, too, we've got shear links in the beam as well. The shear links we use in the bridge beam would really be not substantially different from what would be you may be accustomed to for reinforced concrete bridge beam design too. So again, so bridge beam, pre-stressed concrete bridge beam would also make provision for shear design, shear reinforcement as well. So in order to summarize how pre-stressed, precast bridge beams work, beams are intended to carry flexure as well as shear, but that flexure that they're going to carry results in tension in one face of the beam. Concrete is not good in tension. In reinforced concrete, we use bars, steel bars, but in pre-stressed concrete design, we apply compression in order to overcome that tensile stress in the beam due to flexure. The force is applied using pre-stressing strands. The pre-stressing strands are stretched. Concrete is cast around the strands, pre-tension concrete, and the strands are slowly released, thereby applying that compressive force to the beam while simultaneously applying a moment to the beam that also acts to relieve the applied moment. I should also point out as well, too, that what I've been speaking about here relates to pre-tension, precast, pre-stressed bridge beam design. There is also post-tension bridge beams, which are slightly different, well, rather different from pre-tension bridge beam design.
All right, any questions? Guys, any questions or we're good?
The top part, I forgot what he called it. It's there's like Cambry. I'm not. I forgot. Yeah. Well, that part, that reinforcement is reinforcement, but what is it mostly meant for?
Or
Like,
you
I'll
mean
have
the reinforcing above the beam itself?
Yeah, like that top piece. I'm trying to picture what it's
Okay.
used for, but I'm having trouble.
Okay.
As well too.
Give me a second.
Finally, you'll notice as well too, we've got shear links in the beam as well. The shear links we use the bridge beam would really be not.
Are you talking about the shear links on the top?
Yeah, that.
You know, on the top, you're not going to have just one beam. You're going to have more than one beam, right? Then you're going to have the bridge deck is going to be spanning on the top of it, right? So all of this ties, you're going to put reinforcing right and left. It's going to be across, running across, and also in the longitudinal direction of the beam itself. And then you're going to pour the concrete deck on the top. So to provide this connection between the beam and the deck, you need to have all of this shear dowels, if you like.
Oh, okay.
So this here.
That's assuming that there's gonna be something on top. I mean, like after you get to, I guess.
Yeah, after you put it on the side.
After you put the deck, you don't have to.
You need to have something to drive on, right? So let me see if we put some pictures for it. Okay, after you put it, look, after you put this, you need to have something to drive on. So again, here's some formwork. You're gonna put some concrete deck on the top.
Okay.
Right. So what is the use of pre-stress? Should we continue or take a break? Or you guys already in break? Let me continue. I'm okay with just continue and finish earlier. So what's gonna be the use of pre-stressed concrete? What is the most application that you're gonna see there? Most widely used applications. It's gonna be for concrete piles. Usually concrete piles is gonna be made out of pre-stressed concrete, and they survive more because when you have a pipe, you put the pre-stress, it's gonna be crack-free. And this gonna be the beautiful thing about it. In reinforced concrete pipes, if you just have some reinforcing, it's gonna get rusty easily. If you have some leak, if you have some pressure in it, and then all of a sudden it's gonna open up a little bit, and then just the reinforcing is gonna be gone. 10 years, 20 years, no reinforcing there, and then the pipe is just gonna get bad. It's gonna be in bad shape. But when you have the pre-stress, it's gonna be free of cracks. So it's gonna stay intact. Tanks, big tanks, like big reservoirs, very famous to do with some pre-stressing, bridges, railroad ties, the telephone poles, when they go very high. You have the parking structures, you have hotels usually, because in this type of construction, you're gonna have a kind of systematic, I'm gonna say layout that you can easily just repeat it. And this is when it comes to the mass production, and I'm gonna say here the uniformity of the use of this pre-stressed concrete. Also, piles. I don't know if this is written there, but usually piles, yeah, piles. Pre-stressed piles, very famous. Especially when you put the pile, it's gonna be in the ground and you'd like it to be free of cracks. It's gonna be cracks free. So this is gonna be a very good thing, because if you have chlorides, it's not gonna be attacking the reinforcing if there is no cracks. What is the good thing about pre-stressed concrete, right? As it says here, it's gonna be cracking controlled. I mean, there is no tensile stress in the concrete itself. You are gonna be closing all the gaps. Compression itself is gonna be, you're gonna have lots of compression, top and bottom of the beam. The entire beam is gonna be in compression, no cracks, and this is very good. Better in corrosive environment, because if there is no cracks, where the corrosion and where's the chloride is gonna be attacking the reinforcing inside. So actually, you provide here kind of more protective environment for the reinforcing bars. you're going to have less deflection because at the beginning, you're going to start with some camber. So let's say total dead load deflection, I'm going to say, let's say a couple of inches. I'm just throwing here numbers for sake of discussion, right? Let's say this beam is going to deflect 2 inches for the dead load. Dead load means the self weight and any other dead load that you're going to put on the top of it, right? So dead load only means the self weight in pre-stress, just so you guys know. We have superimposed dead load, which means any other load that you're going to be adding to it. Like what? Like it's going to be concrete deck, any mechanical stuff that you're going to stay there. If you are in the building, it's going to be some of the weight like tiles and floors and ceiling and stuff like this. We call this dead load, superimposed dead load. So what's going to happen? Deflection due to dead load is going to be 2 inches. Deflection due to live load, I'm going to say maybe 1 inch. All right, so you have total of 3 inches of deflection. Let's just say that the 3 inches is too much and you cannot satisfy the code requirements. But in pre-stressed, you can do some camber, and you can camber it, let's say, 1.5 inches at least. You can do 1.5 inches camber. So once you pour the concrete beam, it's going to be going up 1.5 inches. Now you put all the dead load, it's going to bring it down 2 inches, but you have it already, it went up in the camber 1.5 inch. So deflection due to dead load now would become effectively, it's going to be only 0.5 inch, right? And then you're going to have additional 1 inch for the live load deflection. So total deflection at the end of the day in pre-stress is going to be 1.5. In conventional concrete, if you like to use conventional concrete, it's going to be how much? It's going to be 3 inches. So you cut the deflection. Also, another thing about deflection. Deflection is based on moment of inertia. Don't you guys agree? Deflection says equation, let's say for uniform load, WL to the 4 divided by 5 WL to the 4 divided by 384 EI, right? So anyways, it's going to be based on the moment of inertia of the section. Now, when you have no cracks, the moment of inertia is going to be going up. It's going to increase. You're going to have less deflection, right? Because the moment of inertia, right? Increased moment of inertia, uncracked. And the other thing also because of the camber. Also, look what happened. You know that the shear resistance is based on the interlocking between the particles, the aggregate particles, and the cement and the concrete, right? Now you put compression at the end of the beam, especially at the end. This is where it's going to see the most compressive stresses. Now interlocking is going to be greater, it's going to be stronger, which means shear strength is going to be higher than that of conventional concrete beams. So it's going to be actually performance and shear is going to be good. Also, it takes less time wear at the site because usually you're going to buy 3D made, right? You're going to be taking it, just move it to the construction site, install it like steel construction. And don't forget that you're going to be using high strength materials. The pre-stress itself, the pre-stress tendons or cables, they're made out of really high strength materials, 270 KSI, 270, compared to 60 KSI for a conventional reinforcement. And also, don't forget that you're going to be doing tension on the steel. You're going to be measuring out the strain, and also you have the pump pressure. So you do testing, right? You have more quality control. You know that this is going to be a critical issue. I mean, working with pre-stressed concrete, and you cannot just be easy when it comes to properties of materials. So you need to do testing right at the site, and not just testing once. You're going to be testing concrete more than one time. We're going to see the reason of this very soon. Now, what is the bad thing about it? Bad thing about pre-stressed concrete, you're going to have lots of details, lots of analysis, unlike conventional concrete. The shrinkage needs to be considered. In conventional concrete, you don't really care if the concrete is going to shrink a little bit and some cracks is going to happen. In this case, shrinkage is critical because shrinkage means pre-stress losses. This is something that you don't want to see. Also, let's just think about trying to retrofit the pre-stress. How would you do it? You remember the story when I said that some people, let's say a plumber would like to cut a hole in the concrete slab and all of a sudden he sees a cable. Now, if you cut the cable and this is like an elevated slab, not a slab on grade, This is going to be big trouble because what's going to be supporting the slab in this case? You use a pre-stress, you cannot substitute it. But in conventional rebars, you can attach steel plates or you can do FRP easily. So this is going to be very hard to do changes later on. And also in the field, when you apply a certain amount of tension, the quality control really needs to be high. Otherwise, you can lose a pre-stress easily. And this is going to be like big trouble. Don't forget that the beam itself, when it becomes uncracked, is going to be very brittle. Deflection is going to be very small. So no ductile performance. Now let's talk here about the difference in performance between conventional concrete members and between pre-stressed members. This is what you have here in conventional concrete. So this is going to be performance of concrete beams. Here's a beam. You put the typical loads. What are the typical loads? Like service loads, dead load and life load, the loads that you are familiar with. Beam is going to start to deflect. Cracks is going to happen. The force is going to start in the reinforcing bars. You trigger the force. Before you apply the load, this beam is not in use. There is no stresses. If you put this beam here on flat surface, like on the ground, the beam is not stressed. Why? Because you're going to say the entire load is completely supported. You have a complete support right below the beam. No stress in the beam, right? Because you say there is no moment. I cannot draw a moment here. And there is no internal forces before we start to apply the loads. So here, once you apply the load, you're going to build some stresses and tension in the steel and compression in the concrete. In pre-stress, it's completely different. Before you start to apply the load, once you start to put the tension here at the bottom, what's going to happen? You're going to have stresses on the beam. The beam is already stressed. So this is a big difference here. If the beam in conventional concrete is not loaded, you almost have no stresses. But in pre-stress, even before you start to use it, you're going to have tons of stresses. Stress is going to be high. The bottom is going to be in tension. The top here is going to be in severe compression. I mean, severe tension here, and the bottom is going to be in compression due to this pre-stress before you start. Look at this here. Where is the compression? On the top. Where is the tension? On the bottom. This is going to be regular conventional concrete, right? This is the way it works. How about here? Before you start to apply the loads, where's the tension? On the top. Where is the compression? On the bottom. Which means the type of stresses and forces that you apply here is going to be opposite to the conventional service load act or action on it. When we design pre-stressed beams, we design it in a way so that once you put the dead load, the beam is going to be flat. No deflection due to dead load. In here, you're going to see some deflection due to dead load. So here, once you start to put the dead load, you're going to see some deflection. But in here, once you put the dead load, it's supposed to be flat, which is a very good thing. When it comes to the actual use of it, you don't want to see deflection before even you start to use a building under its own weight. All right. We have this partially pre-stressed concrete beams. And in this case, we're going to put some conventional reinforcing with the cable. So the pre-stressed tendons or cables is going to be this yellow line, and the conventional reinforcement, the reinforcing bars, is going to be this light blue lines. When you do your design here, you do your design so that when you put the dead load, the beam is going to be flat. Once you start to apply loads, you may have some cracks at the bottom if you want to, if you allow it. It depends on your analysis, because you can pick and choose. You can say, I want a beam free from cracks, free of cracks. Or I want a beam, it's okay for it to start to crack a little bit, like conventional reinforcing. It's going to be up to you, right? So in this case, you may allow some cracks. It depends on the use. It depends on how do you want to design your beam. Now let's see here what happened when you apply the load in pre-stressed beams. Now this is going to be very critical. This is the point that I was talking about. Point load of an axial load, right? And applied some loading. First, when you apply the loading, any type of loading, dead load, life load, whatever, you're going to have tension here at the bottom. So I'm going to say here is going to be tension, right? On the top, This is going to be compression. So I'm going to say here C. This is due to just the weight, the applied loads. I'm expecting on the top, I'm going to have compression. On the bottom, I'm going to have what? Tension. Now let me try to understand the symbols. F means stress. So F, what? C, which means compression. And this T means tension, not top and bottom in this case. I don't have here this designation FT and FB. In this case, it's going to be compression and tension. And this is due to loading. This is why it says here L. So it's going to be F sub CL. And this is going to be F sub TL. Tension on the bottom, compression on the top. This is just because of the loading. Now let's see here what happened when you apply the pre-stress and the loading at the same time. You see the pre-stress I put right in the middle. And let's see if this is gonna help or this is not good. Now due to the compressive force, I'm gonna have a stress throughout the entire beam section. It's gonna be called F sub CP, which means the force here, the stress due to the force is gonna be all compression. Because of the loading, I can just copy the stress distribution from here. This is gonna be exactly a copy. Just copy it here, right? Now let's do this superposition. Add the stress from the loading to the stress from the pre-stress right in the middle. Negative is gonna be additive. This tension is gonna get reduced. Is this good or bad? Did I do the intended target? Was I able to meet it or no?
No.
Why? What is bad about this?
It's bad intention.
Okay. Here's what happened. Just because of the loading, if you think here about conventional concrete beam, the regular conventional concrete beam, right? You're gonna have this tension compression without you start to add any compression to concrete. And you know that concrete it has a limit. After that's gonna collapse, right? So what you have done here by putting the pre-stress in this location, right in the mid-height, actually you increase the compression of the concrete. And then you reduce the tension on the bottom. So it is true that you did some pre-stress, but the big issue, you added more compression on the beam. What do you mean on the beam? More compression that a conventional concrete beam is gonna see, which means this one. It's gonna be like the conventional concrete beam. It's gonna be stressed this way. So what you have done, you just added more pressure on the concrete. So this is not very good, right? And look what happened here. You just add this value to that value, compression is gonna increase, and the tension is gonna reduce. So you can say here, you can follow this equation or this designation. This is what we also discussed earlier today. How do you find out the stress on the top, stress on the bottom? How do you find out the stress here due to this loading? It's going to be M over S, which moment? Moment due to this loading. And due to compression load, it's going to be negative P over A because it's going to be more compression. So I don't think that putting this cable in the middle is going to be a good idea because you guys have seen it's going to be increasing this pressure a lot. So what we have done here, we decided to put it at eccentricity of E. We're going to bring it down and see what's going to happen. So the stress due to loading is going to stay the same. There's no change here. I mean, I didn't change anything. But look what happened here because of the pressure. This is going to be the pressure due to, look at this, due to the pre-stress. That's why it says due to P. If you go here back in the previous slide, compression here, it was just uniform compression due to the pre-stress when you put the centroid. But in here, it is not uniform. Actually, you start to put compression here at the bottom, and then you start to put your tension at the top, like in here. This is opposite to what the conventional loading is going to be doing. Conventional loading, like conventional beams, is going to be doing compression top, tension at the bottom. This one here, this pre-stress, is going to be doing tension at the top, compression at the bottom. Which is very good, right? Look what's going to happen. When you add this tension to this compression, the compression is going to start to get reduced, correct? When you add to this tension that you have already from the loading, when you start to add this compression, you're going to see here, you may end up with some tension, or maybe you end up with very little compression. It depends on the loading, right? It depends on the amount of pre-stress that you put there and the loading. But generally speaking, you're doing something good. Because based on the conventional loading, you're going to have compression top, tension bottom, and you're doing the opposite. So you're helping out the beam. You're counting, you counteract here the effect of this conventional loading by putting this pre-stress at the bottom. Make sense? Or no, not really. Are you guys there?
Yes.
Yes, that makes sense. It's very interesting how you could just flip it like that.
Yeah, okay. Very good. Now let's look here at the stress equations. F top is going to be equal to what? You just add this to this, right? So this is the easiest way of drawing this beam, and to understand it is that you put the beam, right? You put the elevation of the beam. You don't need to draw the whole thing. You just draw the space, right? And then you start to say, here's the stress top and bottom due to loading. You don't really need to use the same designation here. You can just say here loading, right? Like this. You can say it is due to loading. And this is due to pre-stress. You come here and then you say this area here is going to be due to pre-stress. You do it this way. And then you say this give you the final stresses if you want to. You come here and then say final stresses. You just add this to this and this to that. That's it. And then you redraw it again. And then you see which one was more compression. With that more compression than this tension, you end up with some compression. If you put more tension here than this compression in value, you're going to end up with some tension in the top. Not good. It means that you pre-stressed a lot. Does it make sense? If I put here lots of pre-stress, then what I need, what's going to happen? You're going to have here lots of tension at the top. Not good. And lots of compression here is going to be at the bottom. If you have lots of tension here at the top, to be greater in value than the applied load, you're going to end up with some tension at the top. So the beam is going to still camber. So the beam is going to be cambered anyways. When you buy it, you install it, you use it, and you still see the camber. It's not going to be good. Which means this amount of pre-stress is just too much, more than what it needs. If you put very small amount of pre-stress, you don't really utilize it that much, right? So in this case, you're going to end up with some compression at the top, but it's going to be better than what you'd have done if you just use conventional concrete, because you start here to reduce the compressive stress on the top. And also you start to reduce the tension at the bottom because you put some compression to it. You still can use the same equation that we learned. You just add this stress value to that, add it here, this to that, you add it here. And how would you do the stress here due to loading? It's the same thing, M over S, M due to loading, right? Now look at this moment coming from the pre-stress. It's going to be called E, and here's P, and the moment is going to be called E times P. This moment is different from the applied moment. This moment is going to be used only for the stress due to pre-stressing. So let's look here at these two equations. This is going to be the stress due to pre-stress, and this is going to be the stress due to applied loads, right? So due to applied load, we're going to be using this equation. Because in the applied load, I just have moment. I don't have any axial force, right? Due to the pre-stress, I'm going to have an axial force. Here's the axial force, P. And also I'm going to have moment, which is this P times E. So for the axial force effect on this beam is going to be P over A. And the moment effect on this beam is going to be PE over S.
The S being what? What is?
S, section modulus.
Oh, okay.
You remember the section modulus, top and bottom?
Yes.
Okay. So let's look here at the designation. Due to loading, it says here negative M over S. Is this true? Is it just negative or negative or positive? So I guess I should be able to add here and say negative or positive, right? Plus or minus. Because one side is going to be positive, the other side is going to be negative, like this designation. Anything due to compression is going to be negative, right? When it comes to compression, this is going to be added more compression, so that at the end you'd like to see negative value for the compression. But here, this is going to be tension, right? You add to the compression, you may end up with some tension on the top. Okay. How about the moment, the applied moment? I'm talking here about loading. So I'm going to be taking a piece by piece. First, I'm going to be taking the loading, and then after that, looking at the pre-stress effect. And then after that, at the end, I'm going to combine it and then decide what I'm going to be doing with it. The applied moment is going to be based on the following. Item number 1, dead load. You guys hear about dead load, right? What is the dead load in this case? Remember, dead load is self-weight only. How about this superimposed dead load? What is a superimposed dead load? Can someone tell me what is going to be this superimposed dead load?
Is it like the additional wood and whatever else is used during the construction?
Not during construction. This is going to be superimposed, means it's going to stay there, like tiles, like conduits, light fixtures, equipment, right? All of that. We call this dead load, but it is not part of the self weight. So it's going to be any other dead load. So both of these two is going to be M dead load plus M superimposed dead load. And then I have also M life load. I said, okay, great. So M total is just equal to all of these loads, right? All of these moments. So I'm going to say, where are the load factors? Do you see here any load factors? Why don't you see them? Because I'm not doing here a design for the strength. I'm doing here service checks. You see here, we are doing here check on the stresses. So when it comes to conventional concrete, we just do concrete check, right, for the strength. We do Feynman, right? When it comes to pre-stress, you need to check the stresses at more than one stage. First, when you apply the pre-stress, and then second, when you apply the loads, and then third, when you have the total losses, and then you apply more loads. So in pre-stress, you're going to have more than one service check on the stresses, like performance check. In concrete design, you have only one check. You just do Feynman or PVN, just a strength check. In here, we're going to be working a little bit on working with the stresses, and we don't really care about Feynman for now, because Feynman is going to be so simple. It's going to be somehow similar to what we have done in concrete design. But it is important that we do this checks, we understand it. So when you do service check, you just take the loads as is. There is no load factors, right? And this will be the total moment. Now, when you apply the pre-stress, this could be a question here for you. When you apply the pre-stress, do you have any life load? Do you think you're going to have any life load? Yes? No? No, we're not going to have any life load. You're still in the factory. You don't use it yet. Would you have any superimposed dead load? No. No superimposed dead load. You're still in the factory. All what you have is just the dead load, which means the self weight. And at the time, you're going to have P sub I, the initial pre-stress, the big stress value in the cables, before it dropped down to P effective. So this is going to be one case, one phase, if you like, that you need to check, one limited state. All right, now let's look here at the stress in the top and the bottom when you have some applied moment. Now I'd like here to come up with some equations. I don't like the equation this way. I'd like to have my equation that I can just open my book and use them, right? This is all good, just to understand what's happening, but now I need to develop my final equations. So here is F on the top and F on the bottom, the stress. This P is the axial load, the pre-stress force. Does it say initial or final effective? No, it doesn't. It's just generally speaking. So any axial force divided by the concrete cross-section area. And you see here a negative sign, which means the P here, force, is going to be positive value anyways, right? So you put 100 kips, you're going to be using here 100 kips. You cannot call it negative 100 kips. You just apply it in this equation as is. So just so you know, all the values here that I'm going to be using in my equation, it's going to be all numerical values. You see that? Numerical value, numerical, 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 C. Everything here is going to be numerical. I'm going to be just using this signs, and then at certain point, I'm going to say, did I do a mistake here in this signs, or we're good? So we're going to be discussing this. So I'm going to say, first, it's going to be negative P over A. Yeah, it's going to be compressive stress. I understand. This is going to be from what? From the pre-stress force. Also, I'm going to have another component for the pre-stress, which is due to the eccentricity of the pre-stress cable. Let me look at this. P times E, what is E? I'm going to say, okay, let me go back here. This P times E is going to give you the moment due to the pre-stress. So, okay, this is going to be the moment due to the pre-stress, which means these two components apply by each other. Divide by the moment of inertia, multiply by C. Which C is this one? It's going to be C distance from the centroid to the top of the section. So it should be like C top. So I'm going to be coming to this very soon. Now understand this. In the top, right, when you apply the pre-stress like this, in the bottom, you're going to have compression. In the top, you're going to have tension. So tension is going to be coming from the moment, and then you have axial compression coming from the pre-stress itself. So here we go. Negative for the pressure on the concrete, and positive because you're going to apply tension on the top of the concrete. Now let's look here. Let's extend this and do the bottom one. The bottom stress. What happened to the bottom stress? P over A is going to be negative. And also you're going to have here compression at the bottom. This is why it says negative. Look at this. In here you have compression, right? You have also moment. You have compression due to P, and then you have additional moment coming, pushing it down. So this is why you're going to have two negative components at the bottom. So this makes sense. So this section here is going to be for the pre-stress. So how about this section? What is this term for? You say this is going to be for the applied moment. Whatever applied moment you have, it can be the initial, it can be the final, it can be any combination of this. If you like, you can just say moment divided by IG times C. For the top, it's going to be C top or Y top, and this also is going to be Y bottom. Generally speaking, for simply supported, you're going to have what? Compression on the top and tension on the bottom. So it makes sense. Now I like this signs. I understand them. I can trust them now because we have checked them together. All what I need to do when it comes to moment is going to be positive moment. Just positive value of this moment, right? C is going to be also positive value. All of this numerical values, you just plug it in this equation and it's going to be like positive. This is going to be a good equation for a spreadsheet, actually. Pre-stress spreadsheet, you need to figure out the top stress and the bottom stress. You can just put all of these values. At the end, you're going to tell me whether you have tension, compression at the top. If you have negative values, it's going to be compression. If you have positive values, it's going to be tension. Based on this, all of the signs that I used. We're good? You like this equation? It's going to make our life much simpler. So now you don't really need to think whether it's going to be tension or compression. You're going to be writing this equation, plug in all the values, and all of these values need to be numerical absolute values, correct? And then you figure out the tension compression. Now I'm going to be taking this equation and play a little bit with it. And look what happened. P over A and then PEC over IG is going to be the pre-stress effect. MC over IG is going to be the loading effect. Let's look here. What happened to my equation? You see here, it says F top. What is this? I'm going to say this is due to the pre-stress only. And this one here is going to be due to the pre-stress only. Top and bottom. But let's look here at this. At the initial pre-stress, all what you have is only the self-weight. You guys agree on this, right? This is why I'm going to be using this equation. These two equations is going to be good at the initial pre-stress. So right at the initial pre-stress, you can take this M dead load divided by S top and M dead load divided by S bottom. Just use here positive absolute values. With this, you're gonna have negative because you're gonna have compression at the top and tension at the bottom. This is due to what? Dead load only. Someone's gonna say, how about the pre-stress? Where's this equation coming from? Which is this one here, right? Based on the pre-stress. You can say, let me check here. P over I, PI divided by AC times 1, meaning what? P over A, which means this term here, right? So where's this term? If I'd like to see it in the following equation, it's gonna be this term here, right? This one multiplied by this. How about this term here? If you multiply P times E, is gonna be what? Is gonna be the moment. Look at this. P times E is gonna be the moment. And then you have I, and then you have C. You guys remember this R, the radius of gyration, right? You know how much is this R equals to? You know the equation for it? Let me put it here. R equals, this is something also from mechanics of materials and statics. R equals I over A square root of I over A. Did you guys see this before? Did you take structure steam? Right? Yes? No?
Yes.
Okay. So this radius of gyration, when you say here R squared, you're going to say here, what does it mean by R squared, right? R squared equals to what? Can someone help me?
A over I. I mean I over A.
I over A. Good. So this R squared, just remove it and put I over A, and you're going to see exactly the same equation that you have here, right? And A is going to cancel out with this AC. So this equation is exactly this equation, but we like to put it in this format. So if you like to use something, you can use this safely. So first, I want you to start by doing something like this, and then test it with some given beam, like the same homework that you have done, right? And then you put test compression, and then check your homework. You need to back check your homework. And then after this, we're going to be doing something like this. Look at this. We're going to be doing this equation here. This is going to be for the pre-stress, right at the time of transfer. We call this instantaneous pre-stress force, which is going to be larger than the effective pre-stress force. When you have the instantaneous pre-stress force, you're going to have in the same time only dead load. When you have the effective, you're going to have dead load, superimposed dead load, and life load, which is going to be another check. Let me show you here your homework. Did you guys see it already? And I really want you guys to do this by hand if you like. And then after you do this, you start to do your spreadsheet and then back check your numbers. In this case here, I have this concrete beam. It says 16 by 24. Seems like this is going to be the same beam. And then I have it here in figure 1 and 2. The strength is 5,000 psi. So what happened? Where does it happen? Where does it happen? It seems to me at the beginning of the beam, the cable is going to be right at the mid-center, at the mid-height, right? At the mid-span is going to be at the bottom, and it says it's going to be at 4 inches. Can someone here help me and tell me how much is E eccentricity in this case? And where is E by definition? You see, E
is E equal 8.
E is this one, right? Isn't it?
Is it 8?
Yes.
8? A what?
8 inches.
8. Yeah, I'm sorry. I hear that's A. Okay, 8 inches. Yeah, it's gonna be 8 inches because it's gonna be 24. 1/2. Thank you. 1/2 is gonna be 12. Subtract 4 is gonna be 8 inches. All right. So now I know something here. Here's the amount of E. This is gonna be my E, the eccentricity, if you like. It says here figure 1 at the end of the beam. Yeah, makes sense. And figure 2 is gonna be at the middle of the beam. Yeah, it goes down because I'd like here to develop negative moment to counteract the effect of this given load. Here's the given load. It says here 10 kilograms. It doesn't say dead load, life load. I don't care. This is gonna be just the applied load. Now, do I need to do the self weight? Yes or no? Did you say anything here?
No.
No, ignore it. Let's not make it complex. I just want to do here simple moment. You're going to say the moment equals to PL over 4. 10 times 3300 divided by 4 is 75 kfoot. It's that simple. All right? Take this moment here and then start to answer. First, draw the moment diagram. When you draw the moment diagram, you draw it in the tension side. Did you guys hear this before in your life or no? Draw the moment diagram in the tension side.
Yeah, that's how usually we do it.
What do you mean the tension side? Where's the positive moment? Do you draw it this way? Is this the way you draw it?
Yeah.
No, this is the compression side. You draw it this way. You do it in the tension side. Just imagine if you have a cable, right? Here's a cable. You start to put the point load. What's going to happen to it? It's going to come down. Later on, I may show you very simple ways of doing the moment diagram just by the feeling and do it in the tension side. So where's the tension side? It's going to be here. So you put the moment in the tension side of the beam. If you like to do good design in concrete, this is the way you do it. So actually, the cable is going to be following, this cable is going to be following something that we call elastic line theory. And is going to be following this moment diagram. So your cable needs to follow the moment diagram. If you'd like to do an efficient job or figure out the direction of the cable, the profile of it, it needs to be same as the bending moment diagram. So first draw the moment diagram. Please draw it this way. Don't do it on the top. In concrete design, this is not good. No, this is good for mechanical, good for people, non-structural people. So usually we're going to be in structural business, concrete design especially, you draw it this way. Determine the maximum moment due to loading is going to be this point. Determine the section moment of inertia. You guys can do moment of inertia for this in your spreadsheet. I'm going to say yes. Can you do the section modulus? Yes. Is it top and bottom is going to be the same? Because I'm going to say, let's look here. You're going to have one for the top, one for the bottom. Be sure that you do different equations so that if you like to put a T section, it's going to work fine with you. Because guess what? Next is going to be a T section. And you like to use the same spreadsheet. So start from now by doing it for a T section. Now you do the section modulus. This is simple. Determine the bending stress in the top and bottom of the beam at the minute span due to the applied load. What does it mean by that? You do this due to applied load, which means that you do M over S top, M over S bottom. And be sure that you use negative and positive in your equation. All right? It's going to come like this. And then if the pre-stress force is 6 kips, determine the stress on the top and the bottom in the beam due to the pre-stress force at the end of the beam, which means right here. Now put your eccentricity in the equation, right? Put it like this. Use this equation just to make it simple. Not this. Use this equation here if you want to. Or this equation, whichever you like. You can say use the one that you like, right? But when it comes to eccentricity, make it a variable. When the eccentricity is here, eccentricity is going to be equal to what? Someone help me with this? E equals?
0.
0, exactly. And here E equals 8 inches. I said, okay. Now do the stress due to this axial force, top and bottom. Where? In here. So it's going to be simple, right? You just do it based on this equation, but once you set E equal to 0, you're going to end up with P over A. Look at the equation here. When E equal to 0, end up with what? This is going to be 0, right? So this section is going to get out, canceled. It's going to be P over A times 1. That's it. And then after that, if the pre-stress force is equal to 6 kips, determine the stress on the top and bottom of the beam section in figure 2. Now you have E of 8, right? You're going to have a stress on top, a stress on the bottom. This give you the top, this give you the bottom, this give you this term here. Just do this term. So okay. So what's next? Number 7. It says determine the final combined stresses. This is easy. Just add it from here, right? Combine this plus this. So now actually we didn't add much from last or the previous homework, right? We didn't add lots of things. We just add this concept of pre-stressing force and how do you combine it and what is the best formulas that you're going to be using, which is right here. Remember, this is going to be slide 43. You can use this slide safely. We come to moment, just call it moment. It doesn't need to be dead load or life load. Just call it moment. Come to S top and S bottom. You know how to calculate out. So I have them separate. It's going to be in separate cells of your Excel spreadsheet, right? Radius for gyration, try to calculate out. Do moment of inertia divided by A. So do the A and do the whole thing. Any questions? Yes? We're good?
Yes, sir. For part 7, you said we gotta add F top and
Yeah,
F
just
bottom,
okay.
both
In part,
equations.
you have more than one part, right?
Mhm.
So I'm gonna say here, in part, in this part here, stress at the applied load, this is gonna be part 4. This is gonna be 4, right? This box here. This box is gonna be 4.
Yes.
All right. And then box 6 or box 7 is gonna be for this term here, right? This is gonna be 6, 5, and 6. It depends on the eccentricity. 7, when you add them together, when you apply this equation, you just take this value and add it to this value, or this value subtract, let's say, negative this value, right? You just add them together, top and bottom.
Okay.
It's
And
gonna be fun when you have this spreadsheet because you can play with the numbers quick and it's gonna help you out a lot in the future.
okay. Also, I wanted to know if A sub C is the same as A sub
A,
G.
yes, this is A for
It's
concrete.
all A. Okay. I just wanted to
Usually
make sure.
in concrete design, we use A sub C for concrete cross-section area of the section itself. A sub S for the steel area, right? So
Mhm.
let me give you some stuff here. You can say A sub C concrete section, concrete area. How about AS? Anyone knows AS? Steel area, right? Am I correct?
Yes.
Okay. How about ASP? Sometimes they call it APS. What is APS? Pre-stress area, like pre-stress reinforcing area. Okay. So try to relate to this, please. PI is going to be instantaneous pre-stress. C sub T is going to be the distance to the top from the centroid. R is going to be radius of gyration. I guess you guys, you know this now. Any questions before we go and say goodnight?
Yeah, I was trying to find the homework. Did you post it already?
You're going to see it in a couple of minutes from now.
Okay. And then for the C value, we wouldn't have to like calculate like that formula Fy times, I mean the
You're going to be
grade
using this equation here. But the critical
find
part
out.
is to find out R, which means based on I, so you need to find out I, and try to do it for a T section. You remember this? Try to develop it for a T section like this. Give it variables like PF and stuff, right? And then in this rectangular section, you just do the width on the top is going to be the same as the width of the bottom. This makes sense or no? Yes?
Can you repeat that? Sorry.
Okay. What I'm saying is, if you develop this for a rectangular section, right? And then you put variables. You put, for example, BF, BW for the width, TS for the slab, and this gave you the total depth H of the beam, right? So you can assign certain variables. And then what you need to do, if you like to use this for a rectangular section, right? You can use this BF to be the same as BW in your analysis. Make sense?
Okay. Yeah.
Yeah. So you can still use it, you know, for you can still use it for rectangular section. Any questions?
Sorry, so for C top and C bottom, it would just be 12 since we're doing rectangular?
In the rectangular section, but you need to develop it for something like this. You're going to do here the neutral axis, and then your spreadsheet is going to be calculating it out. But a good check is when you do the previous example, right? That the homework that you have done, you put it in the spreadsheet and you confirm it. You can grade it for yourself. And also you can do it for the rectangular section, and it needs to show you that the depth of the section here is going to be 12 inches, right? C top and C bottom is going to be 12 inches. If it showed you different numbers, you know that something's wrong. Make sense or no?
Yeah, makes sense.
Okay.
So, Professor, do you have example how to do it in the spreadsheet?
In a spreadsheet, how to do it? No,
Yeah.
I leave this to your imagination.
Mm-hmm.
Yeah, I mean, a spreadsheet, you guys know how to do spreadsheets, am I correct?
Yeah, I did in the last class for the project, but I don't know how do you mean by spreadsheet? Do you need like set up all the formula and plug the number in, or how can I set up the spreadsheet for this?
Here's a spreadsheet. Okay. In a second. We're just looking for some spreadsheet so that you know what do I mean by spreadsheet.
Yeah.
Okay, here's a spreadsheet. Look what happened. You can type stuff in here, right? And then you can do some equations. And of course, you can do check stuff, right? If you like to do this pull down menus, if you want to. And then you can do some analysis. You see this equation, which is the same as this equation. You see this equation here? It's not right in here. So you can do lots of stuff with a spreadsheet. You can make it solve it for you. Let me give you something related to what you're doing. I mean, I can have a complex spreadsheet like this. You see how many tabs? And they're all interconnected to each other. They're all walled together, right? So each one of them is reading from the other cells. This is how you have it. So this one, for example, it reads from other locations. Just read stuff from other locations. So I don't want to, but you need to learn stuff like this. I mean, you really need to use it. It's going to help you out in everything, you know. Give me a second. Here's my spreadsheet for this. Right? You put the span, you put the cross-section area, you put, let's say, I, or you can calculate out. And then this can do here the stress for you. It can do the calculation for the stresses. You see the stress F top and bottom? It's right here. You see this and this? You see all of this equation? So you can do it yourself, right? I don't want to give you like an example or give you a spreadsheet so that you copy from it. I mean, this is training for you. This is something is going to stay with you and you can use it later on, if this makes sense. Are we good?
Yes.
All right.
Well, thank you.
Thank you. You guys see homework 3? Just okay, great. All right, guys, you have a good night.
Thank you, Professor.
Please
Take
go
care.
ahead and sign out.
Sorry, Professor.
Yes, hi, yes.
Yeah, sorry. This was just kind of for me. Could you provide the Zoom ID? Because I was like having trouble. I was trying to connect through my phone because my computer, like the Wi-Fi wasn't working.
The
So I was
Zoom
trying-
ID.
Yeah, like on Canvas.
Can you, okay, so you have trouble like accessing Canvas? Is this the trouble that you're having?
Just right